Welcome back to our stoichiometry unit. In today's lesson we're going to be learning how to do calculations that involve starting or ending in the mass of a component in the reaction. The reason we're going to be looking at mass is because problems that begin or end in mass are going to be more realistic. You have balances in the lab, and these balances are not calibrated in moles, but they're calibrated in grams, which we can measure directly, and so we're going to make use of that. We're going to go back to chapter 11, in which we used the molar mass to convert to or from moles, so you'll have to go back and review chapter 11 if you don't remember how to do that, but you'll see a little bit of that as we go through today's lesson. And we're going to find that the mole-to-mole conversions that we saw in the previous lesson are going to remain central to these calculations. So if you're still not sure about how to do the mole-to-mole conversions, I'm going to ask you to go back and look at the previous lesson to make sure that you're good with that. Alright, let's take a look at the anatomy of a problem. Of course, this is going to look familiar as we saw before. As with all these problems, we're going to start with our dimensional analysis. We're going to use that dimensional analysis as our technique to solve the problem. We're going to identify, as before, our given quantity, which we're going to call G, and our wanted quantity, which we'll call W. Now, the quantities may have units of either mass or moles. Next, we're going to make sure we select the correct mole ratio, as before, from the balanced chemical equation. And then as setting up the equation, setting up the calculation, we'll see that we're going to start with our given, and if we have mass, we're going to multiply the mass of the given by 1 mole of the given over the molar mass of the given. Then, going from the moles of the given, we're going to convert to moles of the wanted by applying the mole ratio of moles wanted over moles given, just as we did before. For example, if we have the reaction, my favorite reaction, nitrogen gas and 3 hydrogen gas produce 2 ammonia gas. I want to know if you can determine the number of moles of ammonia produced by reacting 16.2 grams of hydrogen with sufficient ammonia. So let me help you step through this problem. Hopefully we can all identify the given. The given in this problem is our 16.2 grams of hydrogen. Remember what we do with this nitrogen, sufficient nitrogen? Remember what that means? That means we can ignore the nitrogen. It doesn't exist as far as we're concerned. And finally, we want to know our wanted is the number of moles of ammonia. Now notice we're starting in grams. You cannot use the mole-to-mole ratio if you have grams. So let's set up the equation. We want to get the moles of the ammonia. That's our question mark. So we're going to start with our given. Our given is the grams of hydrogen, I'm sorry, so we put the grams of hydrogen here. Now, since we have grams, we want to get to moles. If you remember from chapter 11, we're going to multiply by 1 mole of hydrogen over the grams of hydrogen, the molar mass of hydrogen, 2.018 grams per mole. It's 2.018 because we have H2. Don't forget to get the correct molar mass using the chemical formula. Let's cross off the grams of hydrogen because those cancel now. Now you'd see that we have moles of hydrogen as our unit. So if we keep going in this, multiply by the mole ratio, the moles of the ammonia divided by the moles of the hydrogen. If we cancel the moles of the hydrogen, we're now in units of moles of our wanted. And since we're in units of moles of our wanted, we're done. Do the calculation, and we get an answer of 5.35 moles of ammonia. Alright, so essentially we're doing the exact same thing as before, except the first thing we have to do is we have to convert from grams of our given to moles of our given so that we can make use of our balanced chemical equation and make use of our mole ratio. Alright, let's move along. Now suppose we want to end in the mass. Again, we're going to first identify the given quantity and the wanted quantity. We'll select the mole ratio as before with the correct coefficients of the wanted over the given from the balanced chemical equation. And let's set up those calculations. first multiply the moles of the given by the mole ratio. Since we're starting in moles of given in this case, we can go right to the mole ratio of the moles of the wanted to the moles of the given. Now, that's going to get us to moles of our wanted, but since we're going to want mass of the wanted, we're going to have to multiply that moles by the molar mass of the wanted over 1 mole to calculate the mass of the wanted. And let's take an example, take a look at an example. Our same reaction, we'll change reactions later on just to give you more experience with them. So we're going to start with the nitrogen. We're going to start with the hydrogen, 23.8 moles of our hydrogen. That's going to be our start. Let's set it up. 23.8 moles of our hydrogen is our given. We want to get to the mass of the nitrogen. Since we're in moles here, we can go right to the mole ratio. We want the mass of nitrogen. So the mass of nitrogen is going to have the ratio 3 moles of nitrogen, of hydrogen on the bottom, 1 mole of nitrogen on top. The moles of the hydrogen cancel. Now we have units of moles of our wanted, but we want grams, so we're going to take the nitrogen, the mass of the nitrogen, since it's N2 is 28.02 grams of nitrogen for every mole of nitrogen. Those moles of nitrogen cancel out. We're left in units of grams of our nitrogen, which is what we wanted. So do the math, and we're going to get 222 grams of nitrogen. Alright, now that we've seen what happens when we start with the mass or when we end with the mass, let's go ahead and see what happens if we start and end with the mass. These, of course, are the much more realistic problems, and these are the problems that we're going to be solving in lab next week, in which we have a whole bunch of stoichiometry calculations that we're going to be looking at. Alright, so if both the wanted and the given are in mass, first thing we're going to have to do is convert the mass of the given to the moles of the given so that we can use that mole ratio. Then at the end of the mole ratio we're going to have moles of the wanted, so we're going to have to convert from moles of wanted to grams of wanted at the end. And of course this is going to be done using our molar mass for both the wanted and the given. Let's look at a new reaction, actually one that we saw in the previous lesson. Now we're going to be reacting 4 phosphorus and 5 oxygen to make P4O10, and we want to know how many grams of oxygen are required. So our wanted is our grams of oxygen. How many grams of oxygen are going to be required to fully react with 39.2 grams of phosphorus? Alright, so that graphic came in a little early. Grams of phosphorus is our given. Let's use the flow chart in chart G. I've put together a flow chart for you in which we have our stoichiometry calculations. The mass-to-mass flow chart is the one that goes straight across the middle. We'll be worrying about the solutions and the gases in upcoming chapters. And I'm going to show you how the flow chart works as we go through this calculation. Alright, so first thing we're going to do is we're going to have to multiply the mass of the given by 1 mole of the given over the molar mass of the given. Well, for us the given is an element, so it's pretty easy to calculate the molar mass. We're going to start with the mass of the phosphorus. Remember, we're going towards the mass of the oxygen as our wanted, and here's the beginning of the flow chart. So the beginning of the flow chart is always going to start off with a mass of our given. Right here I tell you to make sure to multiply by 1 mole of the given over the molar mass of the given, because when you do that, when we cancel things out, we can cancel the grams of phosphorus here and here, and the unit that we're now in, if we stopped here, would be moles of given. And this is just like the calculations that we would have seen back in chapter 11. Alright, so far so good. Let's keep going. Next thing we're going to want to do is multiply by the mole ratio, because we now have moles of our given. We can now multiply by the mole ratio. Now, in the flow chart, it talks about B and A as the coefficients. A is the coefficient on the given in the balanced chemical equation. Well, that's just this 4 right up here. So we're going to end up bringing this 4 down here just like we did before. Likewise, the B just refers to the coefficient on the wanted in the balanced chemical equation. So we're going to bring that 5 down just like we did before. and we're going to have 5 moles of oxygen over 4 moles of phosphorus. You notice here's that B telling you to look at the balanced chemical equation, and here's that A again telling you to look at the balanced chemical equation. We're going to cancel now. Let's cancel out our moles of phosphorus, cancel with our moles of phosphorus, and that leaves us with moles of oxygen, which is the moles of the wanted. So this diamond tells us that we're in moles of the wanted. The diamonds, by the way, are meant to help you remember that you're in moles. The squares or the rectangles are mass. And the central calculation, this circle, we multiply the moles of the wanted by this ratio to get the moles of the given, by that ratio to get to the moles of the wanted. That's always our circle, that's always our central calculation. Alright, so if we're in moles of wanted, if that was what you were asked for, you would stop here, but we're not. We next have to multiply by the molar mass of the wanted over 1 mole to go from the moles to the mass. So let's bring that in. Oxygen is a diatomic, so don't forget to multiply by 2 to get the molar mass of the oxygen. Here I'm telling you to multiply by the molar mass of the wanted over 1 mole of wanted. This is just our dimensional analysis at work for us. When we do this, our final answer should be in grams. Cancel out the moles of oxygen, and there's our grams of oxygen. And so all we have to do is our final calculation, and that gives us 50.6 grams of oxygen. That's our mass of our wanted. That's our final answer. By the way, note that if you are given moles of your given, don't convert. Look to see what you're given. If you're in moles of given, you're going to start right here. Right? If you start in moles of given, this is what happened on the previous slide. Moles of given, jump right into the calculation here. We only need to calculate the moles if we don't have it. Likewise at the end, if you are given that if your wanted, is moles, then you can stop here. Otherwise, you have to calculate moles from moles to whatever it is that you want to calculate. Alright, are you ready to try it on your own? I hope so. Your turn. Let's get rid of those. We have a reaction, the combustion of benzene. Hopefully you now are becoming familiar with what a combustion reaction is. Benzene is this 6-membered ring over here, 6 carbons and 6 hydrogens. It's a very flammable liquid, so it does combust very easily. And we want to know how many grams of oxygen, here's our wanted, grams of oxygen, there's our wanted in the equation, are needed to fully react with 84.7 grams of benzene. So, go ahead and try this calculation on your own. I will pause the video now, and after you do the calculation below, go ahead and start it up again and see how you did. And we're back. So, let's go to the calculation. We're going to use the railroad tracks method this time. Here's our wanted, as before, is the mass of the oxygen. Start off with the mass of our given, which is the benzene. Now, we want to go from the mass of the given to the moles of the given. So what do we do next? That's right, benzene, C6H6. The molar mass of benzene is 78.17 grams. So multiply by 1 mole over that, and since we have grams, we're going to cancel our grams here. Now we have moles of our wanted. Now we're ready for that balanced chemical equation for those ratios. The coefficient on the benzene is a 2, so we'll bring that down here. The coefficient on the oxygen is a 15, so we'll bring that down. And we have 15 moles of oxygen over 2 moles of benzene. Cancel out the moles of the benzene here, and we have units of moles of oxygen. But since we want mass, we've got to keep going. Multiply, as before, by 32 grams of oxygen over 1 mole of oxygen. Let's go ahead and cancel out those moles of oxygen, and we'll see that our final unit now is grams of oxygen, like we wanted. So let's just go ahead and do the calculation, and we get 260 grams of oxygen as our answer. Did you get that? If not, go back and make sure that you understand how to work these problems. Make sure that you're always taking the grams of the wanted and converting to moles by multiplying by 1 mole over the molar mass. Then we use the balanced chemical equation, the ratio. Don't forget, this is our B, and down here this is our A. Then we multiply by the molar mass over 1 mole of the wanted, and we get our final answer. Reading for tonight, read section 12.2 in the book, and be ready to come in tomorrow and work on some of these problems.